So in terms of clastic or lithogenous sediments, we sort of have the derivation for these is generally from land surface. We have our clastic rocks, as we studied in sedimentary rocks, we have our conglomerates, a very high energy thing, primarily mechanical weathering. Our sandstones, primarily where chemical weathering has liberated the more resistant minerals from the source rock. Our siltstones and shales, which are very made of silts and clays, where chemical weathering has altered the original minerals into smaller flakes of very easily transported minerals. And so while there is plenty of biological material in these ocean basins, on the continental shelf, this is why we have oil deposits, the overall majority of what's deposited on the continental shelf itself can be thought of as clastic or lithogenous sediments. And so you sort of get this pattern. Very close to the shore, where you have a very rapidly moving rivers, the conglomerates and sands will fall out very rapidly. As you get further out to sea, you get finer and finer particles being deposited on the shelf. So this would make you think, okay, we're just going to get this nice vertical deposit. But the reality is, sea level is going to rise and fall. Because the land generally slopes up as you go inland in most parts of the continents, what you're going to see is as sea level rises, you're going to see finer grade sediments popping up further and further away from the shoreline, or further and further away from the present day shoreline, or further and closer towards the heart of the continent. And as sea level, and we call this a transgressive sequence where your substance and/or is greater than the rate of deposition, or you're experiencing sea level rise. And we have several of these transgressive sequences here in San Diego County from about 46 million years ago to about 40-something million years ago. Years ago, we see like increasingly sediments associated with the increasing distance from the shore popping up further and further inland, recording a sea level rise. Now, because sea level rise has risen and fallen more times than I can name specifically in this context of recording this lecture, you're also going to get lots of times when you see the sediment sequences prograde further away from the heart of the continent. We call these regressive system tracks. In this case, you'll see the conglomerates, the sands, the silts, and all the other sort of more complex deposits moving further away from the shore. So, as we discussed in sedimentary rocks, you do also get plenty of biogenic sediment. Some more common biogenic sediments are made from shells. Shells are made of either calcite or silica. If the shells are microscopic calcite, generally coccolithophores is the most common, or nanoplankton, you're probably going to get something that looks like chalk, aka limestone. You can also get little bits of chert, but these chalk cliffs are fairly common, especially if you go around parts of Texas, but in other parts of the world, or in that case, you're looking at the White Cliffs of Dover. Also in coastal environments, you often see evaporites. Locally, best place to see evaporite sediments is probably the southern part of San Diego Bay by the mouth of the Otay River as you're going through between Chula Vista and Imperial Beach. You'll see all these evaporation ponds, and those are literally depositing sediment as the salt in the water crystallizes during the evaporation process and settles to the bottom of some of those ponds. We see this in more natural environments and generally climates that enjoy hot, dry weather for at least some part of the year. This here is actually a salt lake in Bolivia, located about 12,000 feet, but it's a pretty darn spectacular evaporite deposit. Here's some more. You can also get shells. Larger shells can form it. In Texas, where you don't have a lot of rivers entering the ocean, you get these coquina beaches. This is not from Texas. This is the Salton Sea, also a place that does not have a very large amount of river input on a large portion of its shore. And this is a beach made primarily of shell fragments. Another little picture of chalk. This is a cliff in Texas. This cliff is actually part of a larger bar. I used to get in trouble for trying to climb this cliff because, yeah, I'm a geologist, so sometimes. All right. As we call all these sediments, as we call sediment deposited on the margin, neritic sediment. Here's a river mouth, the Santa Ana River discharging sediment. You can also get wind deposition, or cliff erosion is also a very important source here in San Diego. This cliff, right in these areas where the cliff has collapsed recently, you generally often see a slightly thicker, sandier beach as the waves take this cliff collapse debris and grind it up into more sand. And this is a process that's ongoing. Here we have a river mouth at the mouth of the Tijuana River, and over here we have a collapsing cliff up in, I think, Solana Beach. A little bit more about, and where you don't have river input is typically where you see the most biogenic sediment. It's not that the life isn't where you have river input. In fact, generally there's actually more life there, but all that life gets kind of smothered and overwhelmed by all the fragments of rock. So coral reefs tend to be in places where there's actually not a lot of nutrients. You have these corals which kind of make their own nutrients out of the water and sort of find their own habitat on the rock. The thing about coral reefs is that they can only grow in water depth less than about 150 meters. Once you get below there, there's not enough sunlight to support coral growth. And coral growth tends to be most vigorous in the upper 50 meters of the water column, so that once you're sinking down below here, it's going to be a lot harder for coral growth to keep up with the subsidence. And you can't really grow coral much above the wave line because it just does not like to be above that tide line for any substantial period of time, and is often going to be subject to wave action. Here's some more pictures of, just for entertainment value, some pictures of various plankton in the water. You can see this is actually, the water is actually teeming with it. Here the water's been filtered very heavily to concentrate the plankton. And so what you're looking at is basically filters run through the water and then the gunk in the filter. But this stuff's teeming with life. I mean, all these, if they don't get eaten, which a lot of them do, and if a number of these will settle to the bottom of the ocean, forming the basis of some of the sediment, biogenic sediment you find there. And they come in all shapes and sizes. I know people have spent their entire PhDs looking at like fossilized plankton from the seafloor and telling detailed, vivid stories of Earth history from them. It's exciting stuff. Just you can get silica and diatoms. Probably heard diatomaceous earth. Great for pest control. Great for brushing your teeth. These are all composed of silica. We call these silica shells tests. And they're useful not just pest control, but toothpaste. All sorts of things are built from these things. As foraminifera are made primarily of calcite. So going back to our sort of funky diagram here we have a little teeny island that doesn't really get a lot of rainfall. And you can see little corals are growing along it because there's not much runoff interfering with their growth. If you happen to have a little pond on here that was like exposed that was sort of above sea level at like low tide, this pond might evaporate and give you some evaporites. But you can also see this in dry areas closer to shoreline as well. Now, other sort of phenomena we witness is that there's two major types of biogenic sediment. That made with calcite, which will dissolve in acid, and those made with silica, which tends to not dissolve as readily. As we call and so in medium depth water, all your shells will sink to the bottom, and in places where the water is relatively warm, you're going to get a lot more of these calcareous shells, making a calcareous ooze. You'll see this calcareous ooze will generally be deposited on the mid-ocean ridges. As you get deeper in the ocean, the water gets more and more acidic, and at some depth, known as the CCD, the calcareous ooze dissolves. So even if there's more calcite shells in the water than silica shells, below this depth, you're going to see primarily siliceous ooze. This diagram does a pretty decent job explaining it as well, where you have siliceous tests will sort of generally accumulate in the abyssal plain, and you'll also see siliceous ooze in areas of cooler water, because cooler water tends not to favor calcareous ooze either. I love this diagram. And so perhaps one of the most interesting varieties of chemical sediment is a thing called manganese nodules. Yet in the sea floor, you get some very interesting reactive conditions. You have manganese-rich water in certain places, and over a very slow period of time, these are some of the slowest growing things on the sea floor anywhere. You get these manganese nodules, and weirdly enough, they have a way of sort of like keeping near the surface. You clearly need some fairly slow rate of deposition, but we're not sure why they don't get buried. Manganese is fairly valuable, but they're buried so deep that mining them is not exactly economically viable. So they grow, what they do grow, and you find in certain parts of the Pacific Ocean basin, you see them everywhere on the seafloor. Here's kind of what they look like if you're in a submarine. Here's more of what they look like. These are absolutely beautiful things. So finally, seems kind of rare, but sediments, because the seafloor is a fairly calm place most of the time, anything that falls there that doesn't dissolve along the way gets preserved there. And so we see things like space dust, tektites. We call these cosmogeneous sediments. I'm not saying it's aliens, but if there's any life in the source region for here, it's aliens. It's a small portion of the marine sediment, but we can find it and measure it, and we definitely see some periods of time when there's more of it, some periods of time when there is less. Perhaps the most unusual places on the seafloor are those where there is no sediment being placed down. There's this one spot in the Pacific Ocean, Southwest Pacific, called the Pacific Bear Patch. It's a plateau, so there's no real major sources of sediment nearby. And any sediment does erode off surrounding landforms, gets caught in some of the trenches. There's apparently just enough current to sweep away some of those fine-grained sediments that might otherwise make it out here, borne on the wind or other gentle currents at the surface. And so just think, when you're on the ocean basin floor, you're probably seeing quite a bit of sediment. Thank you very much. This concludes the oceans lecture, and hope you've had a good time. See you.